The Science of Recovery, Post-Hurricane Succession in the Point Pleasant Park Forest. On September 29, 2003, Hurricane Juan struck Halifax, resulting in immense damages to homes and businesses and uprooting 70% of trees in Point Pleasant Park. The park, which was planted resulting in an even-aged evergreen forest, had to be closed for 9 months while it was cleaned up and species diversity was returned. Point Pleasant Park, also known as Amtukati by the Mi'kmaq Nation, was an important gathering place for Mi'kmaq people, providing them a space to hunt, fish, and conduct spiritual ceremonies. Our experiment aimed to explore secondary succession in the park over time using species richness, diversity, and evenness in the 20 years since the hurricane by examining the same 6 sites in the park every year. Secondary succession refers to the process where an ecological community renews itself after an event, with nutrients and life remaining in the soil. We hypothesize that if the park does not experience another devastating event, then it will return to its original community composition with assisted regeneration.
Point Pleasant Park is located on the southern tip of the Halifax Peninsula. Following the hurricane, the park was surveyed to determine the locations of 6 study sites whose forest structure was most impacted by the hurricane. Data collection began at these sites post-hurricane in 2004 and has continued every year to the current day in 2025, excluding the years 2005, 2007, 2016, and 2020. Only years with complete data collection were included in regression analyses. This study uses a repeated measures observational design with no experimental manipulation. In each study site, all living trees equal to or greater than 2.5 centimeters in diameter were measured in centimeter at diameter at breast height, for which the industry standard is 4.5 feet above ground level, and they were identified to determine tree density per species per site. For our method of data collection, we used a diameter tape and a guide of common tree species in Nova Scotia or plant identification apps like iNaturalist to identify tree species. Additionally, percent ground flora cover was sampled using randomly placed 1 meter squared quadrats within each site, excluding trees within the quadrat. Each site is a replicate, and data from all sites are later pooled to conduct statistical analyses on the park status as a whole. Regression analysis was chosen as the statistical analyses because it allows us to test the rate of change in a variety of community metrics over time. It works very well for studies with replicated sites because it can estimate overall trends while accounting for variation among sites. Raw tree data was calculated to obtain total density, richness, diversity, maximum diversity, and evenness. These values were then used to perform regression analyses using RStudio. We used regression analyses of total density, comparison of red maple density to red spruce density, and Pailou's evenness to examine changes in the forest community of the park since 2004.
To examine the overall forest community, we measured the number of individuals of each species at each site every year from 2004 to 2005, as shown in Figure 1. The total density of species increased 23 times the amount from 2004 with an average of 5 to 2025 with an average of 117.2 across the 6 sites. We can predict that the overall community will reach its maximum species richness and density as the forest moves towards its climax community, because there will be younger trees to help buffer winds and support community growth of the forest.
Looking at figures 5 and 6, it can be seen that the density of red maple has increased at a rate of 2.24 individuals per year, which is approximately 6.5 times faster than the increase observed for red spruce over the same 21-year period. Comparingly, the density of red spruce increased at a rate of 0.35 individuals per year, which is much slower than the red maple's rate of increase, indicating that it is less rapidly expanding. These patterns are reflected in both trend lines, which show positive relationships between year and density. This difference occurs because red maple is a fast-growing, shade-intolerant species, whereas red spruce is slow-growing and shade-tolerant. As the forest approaches its climax community, red spruce is expected to gradually dominate, while red maple declines. Red spruce characterizes mature forests in this region as a late successional species, as supported by Jotchem and colleagues in 1985 and Turchin in 2016. Whereas the red maple dominates early to mid-successional stages, especially after disturbances such as hurricanes supported by Burley and colleagues in 2008, and as the light availability decreases, conditions will increasingly favor shade-tolerant red spruce, leading to a shift towards a more red spruce-dominated community.
Looking at this figure, there is not a significantly distinguished trend in the line of best fit. While it shows a slightly decreasing slope as supported by the negative yet small m value in the equation of the line, there are no significant regression results. This indicates that there is insufficient statistical support for the correlation of the data with the best fit line. These results indicate that there was no significant change in total evenness between 2004 and 2025 in the observed sites, which does not align with successional theory and similar observations occurring within the post-hurricane growth in the park. There does exist large differences between sites, which likely contributed to the lack of significance in a larger trend of evenness over the years. This data instead supports the possibility of microhabitats within the differing sites, which could have been caused by differences in environmental factors as well as human activity, like habitat fragmentation and management. As the forest moves to its climax community, the evenness metric is expected to stabilize. Over time, possibly the differences between sites will decrease as the forest matures and stabilizes. In examining the secondary succession of the Point Pleasant forest since 2003 Hurricane Juan, the results of this study predict this urban forest to be at a mid-successional stage. The total tree density is increasing at an accelerated rate over time and has not yet plateaued. The fast-growing shade-intolerant red maple is spreading at a faster pace than the red spruce, a species associated with late succession and shade-resistant slow growth. This restoration has displayed how forest health in an urban context can be affected by numerous factors. This includes the fragmentation of forest habitat by walking trails for park visitors, and also the active management, mostly removal, of important ecosystem characteristics like logs and dead trees for the purposes of public safety. These factors also impact the natural restoration of such urban sites. This could be causing the microhabitat effect unevenness between sites as discussed. In looking at this data and examining pre-existing management strategies, a more informed forest health forward plan can be developed to balance this into recreational priorities. In moving forward, the concept of Edo-Uptimuk, or two-eyed seeing, is a modern-day Mi'kmaq teaching which emphasizes the benefit of multiple distinct perspectives. In using one eye of traditional Mi'kmaq knowledge paired with another of Western knowledge, a balanced path towards improving a reality can be achieved. In applying this to Point Pleasant Park, using traditional Mi'kmaq forest management knowledge and that of local species paired with Western research and methods, this urban park can be assisted in growing into and remaining a healthy Acadian forest for all to appreciate. This requires the significant involvement of Mi'kmaq knowledge keepers and specialists in management, a change which needs to occur now for the health of all peoples and ecosystems.
Yes, the shift in dominant species from 2004 to 2025 can partly be explained by the competition between red maple and red spruce. Literature indicates that each is a stronger competitor under different environmental conditions. Jocham and colleagues in 1985 reported that red spruce had a greater DBH in multiple plots, had a longer lifespan, and was expected to eventually dominate Point Pleasant Park, supporting this interpretation. Red maple is a strong competitor in early to mid-successional stages, so its post-hurricane success is expected, whereas red spruce is more competitive in late successional stages. As the canopy closes and light declines, competitive advantage will shift from red maple to red spruce, which will be consistent with ecological competition dynamics.
Specific examples of the employment of Edo-Uptimuk in conservation practice are few and far between, as this knowledge has only recently been accepted by ecologists. While there exist examples of Mi'kmaq influence and knowledge such as this being used as a guiding principle in ecology study, most involvement of Mi'kmaq specialists and knowledge appears to be purely conceptual and framework-based, rather than using silviculture techniques. This is seen in the establishment of the Mi'kmaq Forestry Initiative by the Coalition of the Mi'kmaq Conservation Group, Unama'ki Institute of Natural Resources, and Government of Nova Scotia, which is using Edo-Uptimuk and cultural lands as guidance and have plans to incorporate Mi'kmaq silviculture techniques in the future. In most cases, projects attempting to incorporate this knowledge and counsel blend it with Western sustainable forestry methods, but fail to include Mi'kmaq traditional forestry beyond a conceptual mission. The consultation of Mi'kmaq specialists and communities has been an excellent way of incorporating knowledge into decision-making and protecting forests, as pictured in the case of Nova Scotia's hemlocks on this slide. In the application of this study, we can move away from invasive overmanagement of the Point Pleasant Park forest through a balance of Western sustainable forestry techniques and Mi'kmaq stewardship principles and native plant knowledge. The idea of stewardship rather than management should be adopted to shift from overmanagement, as discussed in the earlier conclusion, to overseeing through a protective lens that simultaneously recognizes the natural path of the forest. For example, the thinning of the forest should not be avoided but instead balanced. The use of strategic thinning to increase hardwood diameter and size to facilitate old growth under which the rest of the forest thrives. Also, facilitating the removal of non-native species which disrupt ecosystem interactions and growth as a whole. These are ways in which Western sustainable forestry methods and traditional Mi'kmaq silviculture align. In using Western forestry technology and bounding with Mi'kmaq knowledge of species identification and ecosystem interactions developed over thousands of years, a balanced level of management of this forest will contribute to its greater health.
Due to the nature of red spruce and its tendency to be shade tolerant, we can expect that as the forest continues to grow more of a canopy, the red spruce trees will thrive more than the red maple, which is shade intolerant. With this, we can predict that the park will return to its pre-hurricane composition because it will continue to experience succession, which is more favored by red spruce in later stages of succession. We can see the change in composition already beginning to favor red spruce in figures 5 and 6 comparing the species density between 2004 and 2025, where the red spruce has begun increasing in density while the red maple has begun to slow in density. These results support our hypothesis that the park will return to its pre-hurricane composition as red spruce becomes a dominant species.
Young trees act as wind buffers to promote community growth. Hurricanes tend to remove large portions of the forest canopy, but have comparatively minor effects on vegetation in the lower layers. According to Peltola et al., younger sub-canopy trees in forests with multi-stories reduce wind pressures on main canopy trees by absorbing some of the larger trees' movement and help distribute wind energy by slowing and disrupting gusts of wind as they move through the forest. Younger understory trees are more flexible than canopy trees and are able to bend further without breaking, which increases their survivorship in the presence of harsh winds. Higher survivorship of younger trees facilitates community regrowth by helping maintain their direct contributions of seeds and pollen, as well as supporting the seed-dispersing species that rely on them. More densely packed age-diverse forests provide additional stability because their roots interlock, giving each tree a much sturdier root plate area. This reduces the effects of soil erosion in the event of a hurricane. For these reasons, younger trees act as multi-layer defense systems that are critical for maintaining forest health and promoting community growth. First and foremost, the land upon which we collected data, M2Kati, or spiritual place, was lived on and used by the Mi'kmaq Nation for thousands of years before us, and we are grateful to learn on this land. We'd like to thank Dr. Allison Schmidt for her contributions to past data collection, data analysis, and graphs. We're also grateful to Dr. Joanna Zagoras for coordinating data collection, performing our data analysis, and creating the regression analysis graphs used in this presentation. A big thank you to all the TAs and students of the present and past who participated in the data collection in Point Pleasant Park. We'd also like to thank our peer reviewers for their constructive feedback on our presentation. Finally, thanks to Dalhousie for providing the materials needed to collect the data.
These are the references used throughout the presentation. Thank you for listening.